All right, so for question 1 here, we know that we have a mass of neon of 2 kilograms. And we have a temperature initial or temperature of 0.1 of 20 degrees Celsius. And our ending temperature, temperature 2, is 180 degrees Celsius. So right now we know we have mass, change in temperature, and we want to find our change in internal energy. We know that for neon, our C sub V is equal to 0.6179 kilojoule per kilogram Kelvin, or Celsius. This is the same. We can use these interchangeably, which is nice about specific heat. You all took a vote and think this should be an exam question. Yeah. Good luck. Unfortunately, it's not a democracy. But you know, a question like this is likely. So. I was just talking, and you guys probably heard, like, I'm not going to try to trick you. I'm not going to make it much more complicated. I just need to have it be more steps so you can earn more partial credit, or so I can make it worth 20 points. Okay, so we know that our C sub V for neon is 0.6178 from this table 2, right? So we're going to look at neon. We're going to look at our C sub V. Sorry, you can't see that very well. C sub V right there. The reason that I am using my C sub V instead of my C sub P is I don't know that I have well, actually, I'm not told in this question if I have a constant pressure or a constant volume, but I am making an assumption here that I have more likely a constant volume than a constant pressure, since I can assume that there's this neon in some sort of container. If this was an exam question, I would probably tell you a rigid container full of 2 kilograms of neon, a rigid container giving you the hint that it is a constant pressure, constant volume. Another hint, yes, is that you have this like fixed mass here, which gives you another hint that it's a constant volume. All right. It's not like open, you know, letting stuff out. So yeah, okay. So we know that we're going to use the C sub V, and we then have everything that we need to solve a basic equation for change in internal energy. Change in total internal energy is what we're looking for because we want kilojoules. So this equation is our mass times our change in specific internal energy. So our mass times our specific internal energy. We also know that this specific internal energy can be C sub V delta T. We know our mass, we know our C sub V from our table, and we're told our change in temperature. So this question is very straightforward. Our mass is 2 kilograms. Our C sub V is 0.6179 kilojoules per kilogram degree Celsius. And then we have 180 degrees Celsius minus 20 degrees Celsius. Plugging all those in, we get 197.7 kilojoules. On an exam, I would probably make you calculate the mass in a different way, make it a little bit harder by giving you something like density, giving you multiple steps to the problem, or doing something that's a little more earning of partial credit. All right, so here's part A, and then part B. We have, would the internal energy change, so from part A, would the internal energy change be any different if the neon was replaced with argon? And while you could have just looked at your CV value and said, yeah, you should definitely work it out. So if the neon was replaced with argon, what would this energy, change in internal energy value be the same? So for argon, we have a C sub V value of 0.3122 kilojoules per kilogram degree Celsius or degree Kelvin. So if we just work the same equation, delta U equals M times specific delta U. M is still 2 kilograms. U, we can still do as C sub V times delta T. The only thing that's changing here is our C sub V, and it is going down, so it's almost half the specific heat. So 0.3122 kilojoules kilogram degree Celsius. And then delta T, once again, 180 minus 20 degrees. So this gives us 99.9, I have too many decimals, 99.9 kilojoules. Which makes sense because it's about half. So you could have right off the bat looked at your C sub V, said it's about half, that's the only thing changing. My answer is going to be about half, it's going to be about 100. And that logic makes sense. The other logic that is in the solution is if we look at 2 kilograms of neon, how many atoms that is. This is 6 times 10 to the 25 atoms. And 2 kilograms of argon is 3 times 10 to the 25 atoms. So half the amount of atoms. So we have less atoms to be heating up to change 1 degree Celsius. So therefore it makes sense that half the number of argon atoms, so half the amount of argon, has a lower heat capacity, requires less energy to heat up 1 degree. So while even the mass is the same, when we are looking at these actual gases, the amount of atoms are different. So there's less atoms to heat up in argon than there is to heat up in neon. All right, so that is question 1. Hopefully that felt good to everybody. Let's work on question 2. So the egg. And for anybody who doesn't already know this about me, I love eggs. They're a cheap source of protein. They're so versatile. They're fun. The word egg is fun. The color is great. There's like fairy tales about them. They are so wonderful. I make egg bread. I make scrambled eggs. I make frittatas. I French toast. I freaking love eggs. I love them. My friend who's a nutritionist was thinking about getting a tattoo, and I was like, an egg. Get an egg. Like, you have to get an egg. I love eggs. So question 2, let's work on it for the next 15 minutes. I'll start going over at about 12:15. Go ahead. I love it. Hard boiled, over 80, eggs in a basket, like there's like this restaurant in LA that my husband and I would always go to for breakfast, and they have cheesy eggs, just scrambled eggs with crap and cheese. It's just like really fresh out. It is so freaking good. And I saw Pierre Cedric there, the woman who's the closer, she's very heavily bacon. Even cheesy eggs. I was like, anyway. Like even celebrities love those cheesy eggs.
I was devastated. I went getting my car transaction. Well,
What is that? Yeah. No, that's no food. Yeah, I like really thought about getting chickens because of the amount of eggs that I use. We buy them by like the pallet. Like I love it. I was vegetarian for like a year, and I still live like very low on meat. So eggs are just like super cheaper. I love them. Love them. Do you have any questions about them too?
no, I actually didn't get it.
Okay.
I thought I got it, and once I worked on it.
It's pretty similar to question 1, just it's trickier to find mass, and then there's the first. So how are you finding it?
What you gotta do?
Because The density is a heart, so mass is density times volume. And then what are you using for your volume? That's two.
Yeah, and I realized like, oh, it's a sphere, but I forgot what.
Just Google, I mean, especially in class activities, like either ask me or just Google like what volume is. Yeah, that would be on your equation sheet. So for those of you online, feel free to Google the equation of a sphere, and people in class, if you don't already know the equation of a sphere, and that if I needed you to do something with the volume of a sphere, I would put it on the equation sheet. That's not one I expected in my life, but did you look it up? Okay, so 4/3 pi radius cubed. But you're not even radius, you're even diameter. Or diameter. So then, how are you doing your conversion from centimeters to meters?
That's fine. So we got 4 hours to do the same thing.
Okay, yeah, that works. But then you're losing your cube factor. So 10 to the negative 2 cube. And then, so did you get the answer from there? The other.
I always like put it on the side here, so it's kind of like chicken scratch.
Okay.
Like, always whenever you like go over it, I make it more clear.
Yeah, that makes sense. Okay. Well, so you're still gonna use the same equations from part 1, really. Your energy equations will use you with isolating internal energy, and then your internal energy, you're gonna do mass times specific internal energy, and then MC delta T. And this time, are you using CP or CV?
Because it says, hello. Because it's CPUs.
I see where you're going with that, but you don't actually have to convert into your anything at all.
It's just like.
Right, but what phase is it at?
It's the solid phase.
Right, so what is our specific heat for solid? CP, CV, or?
For the solid, it's just.
It's just C, right? So we don't care about constant pressure or constant volume for a solid or a liquid, it's just a C volume. So you can still write CP and just know that that's the P is irrelevant. So because when you look it up for a solid, there's not 2 values, there's just 1 value. But yeah. Okay. You work on part B.
No, that's why I'm gonna stick on it.
Okay, we'll try to work part A. I would first calculate mass, and then I would convert 5 centimeters into meters, and then the rest should be pretty easy. Okay, did you have any questions? I think you're gonna. Yep. Okay. Listen, yeah.
So, I understand
What's heat? Close, but when we're talking about heat here, we're not talking about heat constant, like enthalpy, we're talking about heat like Q.
So,
Yeah.
No, I wanted that 1 minute.
So, I need to have.
Yeah, these questions are really bad. So I would start with that main energy equation, delta E in the system equals E n minus E out. For this one, there's no internal energy, there's no kinetic energy. And so we have just our change in internal energy is equal to the change in energy of the system, which is heat minus work. But we don't have any work going on. So our equation is just or change in internal energy is equal to the delta U equals Q.
Like
Does that make sense what I got there?
Yeah.
Okay. And
I guess
then
I would want to get that. It has to
Yeah.
be systematic,
it
otherwise.
makes more sense like go through it that way for me. And then, so, Q is what we're solving for. What is the Q energy? The Q. And then it says, so Q is equal to delta Q. And we know from question one that our equation for delta U is mass times specific delta U. Specific delta U we can just replace with specific U times two. So essentially our equation E equals MC delta U. And that equation is really, really common. You'll see that on MV. You'll see that like in basic thermal questions, like Q equals MC delta T, that's really where it comes from. But the tricky part of this question is we have Q equals MC delta T. What is it in? Do we have that? How are we gonna do that? Yes.
Because I was like, the diameter, is that not much?
Yes, the name, you're seeing the circle. It's kind of like an oval, but just assume it's a sphere.
So that was the equation.
So
Equation on the side.
you can get a volume, you can get the volume of a sphere, but how does that relate to mass? Right, so what's the equation for density? Yeah, it makes it hard, right? So M over V. So you have density given, you can calculate volume of the sphere diameter. So you just have to look up the volume of the sphere, which is 4 squared pi r cubed. And then you can solve for mass. So mass equals density. And then you gotta be careful converting centimeters to meters. So yeah, the temperature, well, so you don't care about water. So we know water's at 100 degrees Celsius, but we don't really care. We only ask how much heat is transferred to this tank. So we don't really need the temperature of water, we don't need the temperature of water in this tank. Oh, no, this one's not in equilibrium, because we're heating up the water, so they're never really gonna, well, it might eventually come to equilibrium, but.
Doesn't get a sense of the void one to the eggs.
Yeah.
Fully cooked.
But we're not gonna boil the egg, we're converting it. Yeah. Okay. Okay.
I just don't know why.
So it's not infiltrating.
Because this needs, because yes, the 10 to the negative 2 is right. This
Right.
thing needs to be cubed.
Well-
So then you get that 0 value down there. Yeah. I guess
Right.
the first number out there.
I think we discussed that.
Yeah, so,
Yeah, that's what I have.
okay, so
And then you multiply that up by,
what phase is an egg?
by the density.
So does it matter if it's CP or CP?
Sorry, my.
So it doesn't matter. So CP is irrelevant, it's just a state. So you don't have to use your enthalpy equation here. This is where you use that energy equation. So delta energy of the system equals energy in minus energy out. So you don't have to, potential, you just have internal. So change in internal energy will equal to P minus work. You don't have any work. Yeah, there's no boundary work, there's no piston, there's no, there's nothing really, like, the water boiling the steam might eventually do work, but we don't even know that. So it's just delta U equals H. And then delta U, you can plug in for in times specific internal energy, and then C delta T. So it gives you CP, but it's kind of confusing because you have to remember it doesn't matter if it's CP or not. So that's just Q equals MC delta T. And that equation is, if you remember one thing from thermo, it should probably be that, like Q equals MC delta T. It'll be on that, in that sheet. It's like the basic, you probably learned it in front for what? Oh, for the FE, yeah, okay, so MC delta T, like if you have a thermal question, like good chance it's gonna be most of the.
There it is.
Yeah, like if you don't know it, just try to do MC Q equals MC.
Values.
That's a big one, that's it for sure.
Yeah, that's pretty.
Okay, yeah, well, have a great weekend, you guys, head out. Have a good one. Be right back, I'm gonna get some water.
Oh, yeah. Probably used to stay. I think you don't catch me doing that. He's like, no, they won't.
No.
But they do work from home. That's why. The other way is take away. Stop. They do it. Luxury custom at a single time. So they did like Spectra and all those like tires. They propose it.
I've never really.
There was on the news, and it was like one neighbor has hearing and was like like, oh yeah, we're doing it. Probably Maybe a question. They're gonna be good. That's what I mean, we make fine videos, but we don't do vertical. We just want to know everything we install in the ground. It's our job to make sure that. Like, yeah, let's
All right, I'm gonna go over the question 2 in like 2 minutes.
That's when you said, she probably wasn't doing it. That's when you're around your schedule.
All right, let's go over it. Okay, so for question 2, we're dealing with an ordinary egg, even though I would say an extraordinary egg. We're dealing with an egg that can be approximated as a sphere with a diameter of 5.5 centimeters. The egg is initially at a uniform temperature of 8 degrees Celsius and it's dropped into boiling water. So water at 100 degrees Celsius. Assuming the density of the egg is 1,020 kilograms per cubic meter, and its specific heat is 3.32 kilojoules per kilogram degrees Celsius, first determine how much heat is transferred to the egg by the time the average temperature of the egg rises to 80 degrees Celsius, which is a fully cooked hard-boiled egg, yum. And then B, for the heat transfer rate to the egg of 200 watts, which indicates power or energy per time. How much time does it take to cook the egg? All right, so for A, we want to figure out, determine how much heat is transferred to the egg. All right, we have an egg, which is like a sphere, right? So I don't know if maybe you can draw in 3D a little bit better than me. That's horrible, but this is an egg. And then we can approximate this to be a sphere. And we have boiling water that is transferring heat into our egg. So we're making a nice hard-boiled egg. And our egg is almost like a sphere, even though it's a little more oval-like, we can approximate it to be a sphere. We know that our diameter of this egg is 5.5 centimeters. And we know that the density is 1,020 kilograms per cubic meter. We know that the temperature starting, temperature 1 is 8 degrees Celsius. And we know that the temperature final, T2, is 80 degrees Celsius. We know that our specific heat, C sub P, is equal to 3.32 kilojoules per kilogram degree Celsius. And we know that we want to find heat. So I heard from a few people in the class that maybe we're actually looking for enthalpy. But remember, if I were to ask you for enthalpy, I would ask you for enthalpy, not heat. So when I say the word heat, I'm always referring to this Q, heat and work, heat and energy transfer, not enthalpy. Enthalpy is heat content. It is related to Q, but for this problem, we're looking for Q. One thing that I'm going to do right off the bat, because it's the way my brain works, is convert either this to centimeters or this to meters. It is easier for me to convert centimeters into meters, so I'm going to convert this right now, and I'm going to check that the rest of my units seem to be lining up. So it seems like the only unit mismatch I really have is this 5.5 centimeters. So I'm going to convert this into meters. 1 meter is 100 centimeters. Centimeters is one of the easier ones for me because a century is 100 years and a centi is 100. So I am going to convert this into meters. Which is going to be 5.5 times 10 to the negative 2 meters. All right. Then I am going to start my problem. So I will start A over here. For A, we are asked to find heat, but I'm going to start the way that I start almost every problem in chapter 4 with my energy equation. So the change in energy of my system is equal to energy in minus energy out. So the change in energy of my system is my change in kinetic energy plus my change in potential energy plus my change in internal energy is equal to heat minus work, or whatever sort of energy I have coming in minus energy I have coming out. For this one, I know I have heat coming in, so I know I have heat positive, but I do not have any work happening. I don't have any, piston moving. I don't have any turbine spinning. I don't have any fans. I don't have any work happening. I also don't have any kinetic energy or potential energy because I am a stationary boiling pot. So my equation becomes my change in internal energy is equal to heat. I know from question 1 and from work that we've been doing this week that I know I can change my change in internal energy into the equation of M times specific internal energy is equal to heat. And then my specific internal energy here, I can convert into C delta T. So if you notice here, I'm not putting C sub P or C sub V or C sub anything because my egg is a liquidy substance that's turning into a solid, which are both incompressible fluids. So for this C here, my CP is equal to my CV is equal to my C. The specific heat values at a constant pressure or a constant volume are going to be equal, and they are the same for any incompressible substance. So it's a liquid or a solid. So my equation is now Q equals MC delta T. This equation is the backbone of thermodynamics. For those of you in my funnies class, and I think in Carotons as well, you've already learned this. This will probably be on the FE in at least one question. This is definitely in your FE handbook because I've taught an FE review for thermal before. This is an equation. If you ask my dad what he remembers about thermodynamics when he took it back in like 1982, he remembers Q equals MC delta T. MC delta T is a very, very common equation for basic thermodynamics. So heat is equal to mass times specific heat times change in volume. All right, so now we can start trying to plug into this equation. We know our change in volume, we know our specific heat, so we know these two, but we don't know mass. So when we're looking at an egg, what sort of information do we have that's related to mass? Well, we know that we have a sphere and we have a diameter, so we can get the volume. And we know we have density. And if you remember, density is a heart, which is mass over volume. So density is mass over volume, which means therefore mass equals density times volume. We're given density, we're given information to solve for volume. So therefore our equation can become Q equals density times volume, C delta T. Our equation for volume of a sphere is 4/3 pi r cubed. We don't have r, we have diameter, which a diameter divided by 2 is r cubed. C delta T. So we have density, we have diameter, we have C, we have delta T. So we should have everything that we need to plug in for this equation. So this equation becomes 1,020 kilograms per cubic meter is our density. Then we have 4/3 pi, our diameter, which is 5.5 times 10 to the negative 2 meters, divided by 2 to get radius cubed. Our C value, which is given to us to be 3.32 kilojoules kilograms degrees Celsius. I'm going to run off the page. So then our delta T times our delta T, which is 80 degrees Celsius minus 8 degrees Celsius. So my Celsius is going to cancel, my kilograms are going to cancel, my cubic meters are going to cancel, and I'm left with kilojoules. Q should have units of kilojoules, that should make sense, that's great. When we plug this all into our calculator, we get 21.24 kilojoules. All right, are there any questions about MC delta T, kilojoules per kilo, or how to get to this energy unit for heat? So I would also write, positive transfer to egg, even though in the question it is telling you that, right? So your answer should already be what is transferred to egg, because in the question it says how much of the heat is transferred to the egg. So it's defining your system kind of for you. Negative and positive becomes a little arbitrary here, but if we're considering our egg to be our system, then we are saying that Q coming into our system is positive. All right. For part B, we are interested in figuring out time. So for part B, we have the same egg condition, but we know that the rate of heat transfer, rate implying a per time term, is 200 watts. This is our rate. We know that 200 watts is going to be 200 joules per second, because a watt is a joule per second. So 200 watts is 200 joules per second. We know from part A that our heat transfer is 21.24 kilojoules, which is 21,240 joules. So now I have joules per second. You can see how the relationship between these is gonna give you time. So if I have 21,240 joules divided by 200 joules per second, then my units that are gonna be left are gonna give me seconds. And this is going to give me 106.2 seconds, sorry. Another way you could do this would be to, here's a big or, you could do 21.24 kilojoules divided by 200 watts, where there are 1,000 watts in 1 kilowatt. Kilowatt giving you kilojoules per second. So once again, your unit should be seconds. This works out to the same thing. So you can either convert watts to kilowatts or kilojoules to joules, whatever works best for your little brain. Okay, so that is all that I have for today in terms of the problems. Are there any questions? Okay, well then, why don't you spend the next 20 minutes of class, the last 20 minutes of class, starting to study for the exam? Particularly those of you, I think there's several people who have multiple exams coming up next week. So please use this time to go ahead and start studying. Have a great weekend, and I will see you on Zoom on Monday. Have a great weekend, everyone.